Hello everyone, my name is Shaohua Li, and this is a joint work with TU and Zhendong. And today I'm going to present our work on boosting compiler testing by injecting real-world code. And my talk is going to be like this in this framework. So first of all, let's look at the background and the related work. So compilers, they are supercritical infrastructure software systems that help us translate whatever code we write in high-level language down to some machine code so that we can execute on different platforms. But despite its criticality, compilers they may also have bugs leading to for example, compiler crashes or even miscompilations to affect the functionality of the software or systems that rely on the compilers. So let me give you an example. So in this example, on the top there's an activate function that takes two integers as input and returns some integer. And we are calling this function with some inputs at the bottom. So because the first parameter is greater than the second parameter to the activate function, so the return of this function of this program or the output of this program should be equals to 0. However, if you compile it with GCC 12, GCC 13 with some optimizations 01, 02, it will tell you the result is 1. So what happened? So the root cause is because of a bug in the GCC optimizations, which incorrectly translate the code, the activate function, to some max operations, which is erroneous and incorrect. So such a miscompilation can potentially affect a lot the functionality of many software systems. So we need a reliable. So we need to validate the compilers. And because of the super complexity of compilers, one of the most important tool to validate compilers is to do testing. So here's the general framework to do compiler testing. That is, we first design some program generators or random program generators that can generate a set of different programs. For example, a set of C programs to test the C compiler. And these programs, they are designed to be valid. And then we can pass them to the GCC LVM clan so that these compilers, we can get a set of executables and to verify if these executables are correctly compiled by the compilers. So the most critical component in compiler testing is about how to generate those programs. So how does the existing work generate those programs? Well, most of them, they directly or indirectly rely on the rule-based random generation, meaning that we have a set of predefined rules or a set of hard-coded rules. For example, when we're generating a new program, we first query some rule to generate, for example, some variable declarations. We query the loop rule to generate some for loop, and then generate some if condition, if got, and then a while loop, so on and so forth. So in some sense, the random generation is really, really powerful. They can generate a large volume of valid programs and to extensively test the compilers. However, because of their constraint limitation, the expressiveness of the generated programs, they are constrained, because if you check those programs, they are of they look somehow very similar. For example, here's a loop from Systemis. Systemis is a pioneering random program generator for C compilers. So it generates some for loop, but it always being constant bounded, meaning that, for example, this P1 always less than 6. And here's another loop from the Yapgen Ver2, which is a more recent random program generator. And although this for loop seems to be more interesting, involved some variables, but somehow these variables, they never been changed inside the loop body, meaning that those loops, they are having the fixed patterns and they are all bounded. And now let me show you some new loop on the right hand side. And this loop, the loop body, first of all, syntactically, it looks very different from all these two loops from existing random generators. And this loop guard, the B variable, is not bounded. It's not constant bounded, and it is constantly modified inside the for loop. So meaning that this loop has some complex semantics and some unbounded, and it is unbounded. So, but they are not somehow supported by those loops. So the key question is, how could we generate the more expressive code, just like what I've shown you in the previous slide? Well, the motivation of our approach is that we need to ask why do we need to generate various programs? Because we want to use these programs to validate the compilers. And why do we do such a compiler validation? Because we want to make sure that compilers, they do not make any mistake on the real-world code. Because those real-world code, they are really diverse and they are really complex. Yes, this is real-world code. They are diverse and they are complex. So our own unique vision and our view to this program generation problem is that why can't we use this real-world code to validate the compilers? So this observation motivates our approach, that is to utilize the massive power of open source code. Because the open source code, they have diverse features and they have complex semantics. For example, the for loop, this complex for loop I just shown you is actually I just copied from the FreeBSD on GitHub, and this kind of loop can never be generated by the existing random generator. It's really hard to be randomly generate a loop like this, especially without any undefined behaviors. So next I'll show you how we utilize the real-world code. So in one sentence, we want to inject those real-world code into random programs to boost their expressiveness by using those code features that are not yet supported by the existing random generators. So for example, we first have some random programs. For example, we have some random programs, and then we want to have some codes from somewhere, for example, from GitHub, and then we want to inject them into the random programs to get the new program, which we can then utilize to test the compilers. So next, I will first show you how we get those code from the GitHub. So we call this an offline procedure because we can collect it just offline, and we want to, the target of this procedure is to construct a function database. So the first step is extract functions. We want to extract all kinds of functions from the GitHub, and we are talking the C programs. So for example, we can extract the activate function. So we extract the code at the granularity of function because it is easy to control their behaviors, and to control their behaviors to model their semantics. And we extract all kinds of functions from the GitHub. And then the second step is called I/O inference, meaning that we want to get the I/O behaviors of the functions. For example, for the first active function, we can generate some inputs to see what's the output behavior of this active function. For example, we know that whenever we call this function with 0 as input, we know that 0 is output. So we can get multiple I/O behaviors for this one particular function. So after doing those I/O inference, so we can construct our function database. So the function database is nothing else but just the caching. We cache all the functions together with those I/O behaviors, which can then be utilized in the next step. So in our current implementation, we extracted over 50,000 functions from more than 100 most popular C projects hosted on GitHub. So next, I'll show you how we inject those real-world functions and into some random programs. So this is so-called online procedure. That is how we generate new programs. So firstly, we get some random programs. So here is a toy example with a few lines. The second step is we want to profile this program. Profile meaning that we want to get the desired meaning or semantics of the programs. For example, after profiling, we can know that at a particular location, for example, at line 4, we know that there are two variables available at the line 4, which is the global variable value and local variable a, and their respective values. And then we do some matching. Matching means that we want to find some particular expressions in the random program that can further be substituted with some real-world code. And then we select some functions from the function database that we cached before, so that the return type of this active function match the expression from the last step. So next, I'll show you. We introduce a synthesizer, and which I will introduce how we insert the active function into this random program. So first, we just place the random program as it is in the new program, and then somehow we find that the 0, the match expression 0 is 0. and the active function also returns 0 onto some input. So we can safely replace this 0 with the active function with these two inputs, right? So, and then we place these function definitions to make it compilable and runnable. So at this point, this new program actually has already combined the random program with the real-world program, but the semantics is exactly the same as the previous random program. And further, we can make this more complicated. For example, we find that somehow the first parameter to the active function is 2. The global variable is 2 at this line 4. So we replace this 2 with a global variable to build some data dependencies between these two pieces of code. And we can further do it. For example, we realize that the 0 and is also the 0. The second parameter 0 can be substituted by somehow a minus 0. So at this point, this program can then be utilized to further to test the compilers. So the core gist of this approach is that we want to merge multiple code or functions that we crawled from the real-world projects and trying to inject them into the random programs. But most importantly, we want to build the complex data flow and control flow dependencies by utilizing and fusing different variables. And with this new program, we can go test the compilers. So next, I'll show you some evaluation result of our approach. So we implemented a tool called Serial to implement all the ideas I just presented. And we use the Sysmees as an underlying random generator to generate all those random programs. And we use extracted 50,000 functions as a function database to drive our approach. And here is some statistics about the functions we extracted. So on average, those functions consist of 17 lines of code. So the most critical and important question is that how many compiler bugs can our approach, our Serial, find? Well, we use Serial to fuzz the GCC and our VM for 9 months. So here's the result. So in total, we reported more than 130 bugs to the GCC and LVM, and more than 100 of them have already been fixed. This means that our Serial can find many new compiler bugs in those production compilers. And then we need to understand what kind of bugs we can find. So we classify those bugs based on their symptoms. For example, symptoms. So then we find that either it's a crash or it's a miscompilation. So we find that 53 of them, they are crashes leading to some compiler crash, and 79 of them, they are miscompilations, meaning that the compilers, they made mistakes during they emit faulty code. So more than 60% of all the bugs that we found, they are miscompilations. So that led to a second finding that the Serial can find many miscompilations in production compilers. So we also look at those bugs that we try to analyze the bugs, like how long the bugs have been there in the compilers. So here's the plot that we analyze 10 versions of compilers for GCC and LVM to see how many bugs we found can affect the correctness of those compilers. So we find that many of our bugs can trace back to the older versions of the compilers. For example, in the GCC or on the left-hand side, there are even 2 bugs that affect GCC 5. Right now we are using GCC 14 or something. So that means that these bugs have been there for 5 or even longer years, 10 years or something. So the third finding is that our Serial can find many long latent bugs. And then we also measure the Serial, does Serial increase the code coverage? So we generated 10,000 programs using both the default random generator and also our new tool. And here's the result. We show that on Serial, on both GCC and LVM, our new tool, Serial, significantly covered more lines than the random programs. For example, on GCC, we covered 3.6% more code. But if you know that the GCC LVM, they have tens of millions lines of code, that means that we covered more than 30,000 more lines. And on our VM, we covered more than 40,000 more lines. That means that if you treat this as some kind of the expressiveness of underlying program, that means that our serial can successfully boost the expressiveness of the underlying random programs. So let me give you 2 examples about the bugs that we found. For example, on the left, this is some program we generated, and this is a real function. This function is actually is doing some bit reverse, try to revert the bit stream of the input variable, and this is from QMK firmware. And this bug triggers GCC miscompilations in many versions, because the GCC want to do this very efficiently but incorrectly. And they just have some specific optimizations for the bit reverse function, but somehow this function can never be generated randomly, right? And here is another example that is also from the FreeBSD, and it takes some integers as input, but somehow it is casting the integer into some pointers and trying to use that pointer again inside some while loop, some unbounded while loop. That lead to some miscompilations again in the GCC. So in conclusion, I have introduced a new way of boosting the expressiveness of the random programs by injecting the real-world code. And our new tool has found a lot of new bugs in the production compilers, especially most of them, they are miscompilations. And that's all. Thank you. I'm ready to take questions.
Thanks for the great talk. There's one fundamental thing I didn't understand. So you said you do this value inference for the functions that you extracted.
Mm-hmm.
But when you do that, you need to compile these functions too, right? And then how do you know that these were compiled correctly?
Mm-hmm.
You
Okay.
don't, right?
Yeah. So thanks for the question. So we are trying to look at the function signature and trying to generate some driver functions.
Mm-hmm.
Driver function means that there's a main function that correctly initialize some variable and try to call that function.
Right.
So we then compile this whole as a whole program to know whether or not this is compiled and whether or not this is correctly behaved. Like if there's no undefined behavior, if I call this function with this input.
Yeah, but the compiler that you use to compile then that code that can also be flawed, right?
Yes,
and then,
exactly,
then you have a
exactly,
wrong data
exactly.
set, right?
So our assumption is that we want to use multiple things, and actually we did that. That if we don't use random programs, just use those programs, can we find the compiler bugs? But actually, it's very, very rare for both GCC and LVM make the same mistakes.
I understand that. All right, thanks.
And thank you.
I think I have a somewhat related question,
Okay.
sort of. So I'm curious if you did anything, when you found these functions, if you did anything to guarantee that the functions were pure, or at least had no side effects to global variables. And sort of on a related note, you're pulling out functions and maybe assuming that the compiler is going to inline them. Did you consider, or are you looking at chunks of code that aren't necessarily contained in functions that you might instead inline yourself?
Okay, thank you very much for the question. So for the first one, how do we know if we guarantee the function to be pure? Yes, we need to guarantee all the functions in that we extracted they are pure, meaning that we can fully model their behaviors based on input-output. If it's not pure, for a lot of functions they are not pure, we have a set of transformations and trying to remove or transform it to make them become pure functions. Yeah. So for the second one, so what was the second? Sorry.
Yes, okay. The second question was, have you considered looking at chunks of code that aren't necessarily contained in a function? Because it seems like likely a lot of the optimizations here are the compilers inlining the function and maybe doing it incorrectly and trying to optimize. I'm curious if you looked at any chunks of code that you didn't pull out as a function, but just instead inserted directly into.
Yeah. Thank you very much for the question. So we've tried that. We tried different attributes. For example, we can force the compiler to inline some of the functions, but we didn't inline them by ourselves. But we can of course do that, but we didn't do that. Yeah. Thank you.
Last Yeah, very interesting work. So I got two questions actually. So first is when you trying to extract the functions, do you have any preference? Like you want to extract functions with complicated loop inside, or it's just a random strategy here? This is the first question. And second question is, it looks to me the example shows all these functions are like the argument and return type is a single basic types. So what will happen if they are like types like struct or even nested complicated data type?
Okay, thank you for asking. So for the first, let me answer the second question because I forgot the first one. So the second question is that do we support other types? Yes, we support pointers. For example, we have some big pointers, they are not pure. We have some mechanism to transfer them into a pure function. But we do not support more complicated functions like structs, for example, because that's very hard to model them. So I suddenly remember the first one. The first one is that how did we favor some complex functions? No, we just extract every possible functions we can extract it from those 100 most popular open source projects. But in the paper we indeed analyze which kind of functions that actually help us finding more bugs. So we actually analyze those functions that help us find a lot of bugs, which indicated that if we want to improve the random generator, which directions should we go? Okay, hope that answers your question. And thank you all for attending this
Let's
talk.
thank the speaker once more.